Test 1, 2, 3. Test 1, 2, 3. Thanks. All right. I see about 1, 2, 3, 4, 5 students. So until we wait for the others, perhaps you've seen the Big Bang Theory, and on this PDF you can find these molecules, which is red. This is a link, so you can check what Penny did when she wanted to look like a scientist but found the physics or science too boring to attend the courses. So if you also think that it's too boring to attend, you can have some idea how you can look like a scientist. This is a 2-minute video. Perhaps your classmate will appear, but if not, we can really start the lecture. Just check it. I will try to write on the table. So this is lecture 4. Alright, what we learned before, how to calculate from the xt the position along the x-axis. You know, describing any motion, we need a coordinate system. In the coordinate system, we can have the x projection of the motion. The xt can be anything, but from that, dividing by time, you can have the velocity, or more precisely, the x component of the velocity. And if we derive again, we can have the x component of the acceleration. So, deriving the function xt, we know the velocity and then the acceleration. Since physics, we have mainly laws for forces, and from the forces, let's say again the x component of forces, we can have the acceleration by only dividing the x component of the forces by the inertial mass, which is the normal mass. So technically, we will follow the following route. From force we can have the acceleration, from acceleration we can have the velocity, and the velocity we can have the position of the particle. In 3 dimensions, so that was the 1 dimension, we practiced a lot, and in 3D, since the r, the position of the particle, can be expressed by the xt, yt, zt, if we want to follow the rule from position to velocity, from velocity to acceleration, we have to play with 3 time-dependent function, xt, yt, and zt. And if we want to have the velocity from the position, we have to derivate component by component to have the vx, vy, and vz. And technically the v is the vx, vy, vz. Alright, how can we do that? You can see an example on the next slide. For example, I take a screenshot of it and clear the table. So what if I know I have a point-like body in the 3D. It's expressed by xt, yt, zt. You remember the unit vectors of the coordinate system? This formula is equivalent with the xt times I plus yt times j plus zt times k, and these are the unit vectors, so these are perpendicular to each other. These are along the x, y, and z axis, and technically these are unit vectors. In every coordinate system we can have unit vectors, and this form is simply equivalent with each other. So let's see. You can see on the presentation we have a 3t squared minus 2t minus 5, and yt is a 2t plus 1, and zt is 2. You can think about how this particle moves. So for example, we can ask where the body at 0. So what is the initial position? You can calculate. So it's minus 5, minus 1, and 2. So how can I calculate where is the body at t equal 2 seconds? Of course, you can do it easily. So 2 seconds. It's 3t squared, which is 4 times 3, 12. So it's 3 times 4 minus 2 times 2 minus 5. 2 times 2 plus 1. Oh, sorry, it's plus 1. And 2, which is 12 minus 4 minus 5. It's 3, 5, 2. So calculating where is the body at t equal 2 seconds is easy. Why don't we calculate the velocity? Velocity means we have to derive the xt, which is, I'm pretty sure you know it, it's 6t minus 2, the vy equal 2, and the vz, since the x position, the z position is a constant, the constant has 0 result in derivation, so it's 0. So the v, how depends on t? V depends on t only in the x projection, the rest is constant. With similar, yes, and for example, we can ask what is the velocity at t equal 2 seconds. It's 6 times 2 is 12 minus 2 is 10 to 0. These are the examples you will find in the first test. I will give you a 3-dimensional motion, ask where is the body at given time, what is the velocity at given time, and what is the acceleration at given time. Make a photo and calculate the acceleration. AX is the only interesting because AX is dividing VXT by T, which is 6. The rest, since these are constant velocities, are 0. So the acceleration technically at any t is a constant. So if I ask what is the acceleration at t equal any time, so let's say t equal 2 seconds, this is just the same since this is a constant. We know the Newtonian law F equal m times a, so we can ask what is the body, what is the force acts on this body if the mass, let's say it's 1 kilogram, the F is like 6, 0, 0, and you know these are newtons. And of course, since the force is a constant, that will be also at any time, so for example at t equal 2 seconds. That was the easy way, so let's calculate the displacement vector from the acceleration and from the boundary conditions. You know boundary conditions, for example, where is the body at given time, usually we will add the position and the velocity at t equals 0. So how it works, let's say acceleration is 1, 2, 3, and we know at t equals 0 we are in 3, 0, 0, and the velocity at t equals 0 is 1 over 2. How can we do that? You remember the velocity is the time integral of the acceleration, so technically on the graph, if we have, let's say, the ax versus t, if I integrate something from t initial to t final, the area under the ax is the delta vx. What does it mean? Sorry, I will replace in the first integral, the vt equal integral from 0 to t a dt. There we have the delta, capital delta, vt. So let's do it component by component. So for example, how the x component changes, and I will replace the ti with 0, and the tf is normal t. That means I won't ask where is the body at given final time. I want to know it for any time. Delta Vx is simply from the initial point to any t, and have to integrate the ax dt, since this is only 1. The primitive function of 1 is t, which is t minus 0, which is t. There are lots of t here, so we know the delta Vx is simple the 1 times t. What does it mean for the Vxt? Is Vx t equals 0 plus delta Vx for any t, which is 3 plus t. You see the 3 comes from the initial condition, and the t comes from the integral of the ax. Oh. Alright, I will change. Here I add the initial condition of the velocity and not for the time. I will create a new PDF, new example. Alright. Vy is simply 0 to t the ay, which is integral the 2 from 0 to t, which is 2t, the Vy t equal the, oh no, sorry, no, I went the velocity, and the PDF is true, I missed it on the table right now. So that here I have to add the Vx at t equals 0, which is 1. So this is the boundary condition for V. Alright, so what is the Vy at t equals 0? Plus add the dVy. Since the Vy at t equals 0 is 0, this remains only 2t. The Vz, when we integrate to the Az, which is 3, so this is the Vz at t equals 0, that's 2, plus integrate from 0 to t the Az, that will be 2 plus 3t. Alright, let's save somewhere the V. T will be 1 plus t, 2t, 2 plus 3t. I clear the lower part. And let's go to calculate what is the displacement vector. If I know the Vx, for example, how it depends on t, the dx, the delta x, the displacement, is the integral of the Vxt. So xt will be the x at the given boundary condition plus integral from 0 to t the Vx, and that will be 3 plus, this is t plus t squared, the primitive function of the 1 plus t from 0 to t, which is 3 plus t squared. The yt will be the y at t equals 0 plus the integral of Vy, which is 0 plus t squared. Let me check again. I think, yes, I missed the 3 from here. Alright. Which is t squared, and the zt equal the z at t equals 0 plus integral the 2 plus 3t. Yes, I think I missed again the t over 2, t squared over 2. So, which is z t equals 0 is 0. The primitive function 2t plus 3t squared divided by 2, which is 2t plus 3t squared divided by 2. Alright, so the RT will be the following: 3 plus t plus t square over 2 t square and 2t plus 3t square divided by 2. So that will be the result how a particle moves, which has the constant acceleration 1, 2, 3, and the initial condition at t equals 0 it's 3, 0, 0, and its initial velocity is 1, 0, 2. On the presentation, I will add the plus 1 here, now the plus 3 here, since it has a initial 3 at the beginning. Alright, so that's about how to calculate from acceleration the displacement, how to calculate the displacement from acceleration, derivating, integrating. We will practice on the seminar if you need more. Let's talk about forces. We can talk about equilibrium, which means the sum of the forces must be 0. If you look at your phone, which is, for example, next to you on the table, there is a gravitational force on the phone, and also there is a so-called anti-force from the table, and these must be the same in magnitude and opposite in direction. So how can we calculate the forces on a body that doesn't move? Yes, it's reaction force. Let's calculate something. For example, if you have a 5 kilogram body and you fix it to the ceiling with a wire or something, and if this is 45 degrees, how can we calculate the forces on the string? We know there is a weight which is 5 times 10, like m times g. This is 50 Newton. So equilibrium means the sum of the forces 0. We will solve it by adding along the x and along the y. At first you have to say which is the x, which is the y. Let's say this is the x and this is the y. What are the forces along x? So for example, this is the point A, this is the point B. I can talk about FA and FB. What is the x component? Again, like x projection, FBX. And what is the x projection of the FA force? This is, since this is 45 now, this is simple. No, let's calculate it. So these are the alpha. These are FB times sinus alpha, which is 45. You remember this FB can be also here, FAX. So this is the opposite part of the triangle, and this is positive. If we say this is the positive x direction, which is signed by the arrow on the x-axis, it's a positive force, plus I have to add the FAX, but look at it, since this goes opposite to the x-axis, that will be minus FA times sinus 45. What does it mean? So this has to be 0, since the sum F equals 0 means the fx and also the fy has to be 0. That means fb sinus 45 equal fa sinus 45. If we only divide with sinus 45, we can say fa equal fb. And that's enough for now. Let's check the y. Since y goes upwards, at first we have a minus 50 Newton, which is the weight. And this has to be compensated by the y component of the forces. These are positive, so this is plus fa times cosinus 45 plus fb times cosinus 45. That has to be 0. But since we know fa equal fb, so you can replace this fb with fa, means we have 2fa times cosinus 45 equals 0. 2fa times, let's calculate, this is square root 2 over 2 and divided by 2, this is 50, sorry. And what it said, so if you multiply with 2, this is 100, then divide with square root 2, 2fa equal 100 divided by square root 2. Let's divide again with 2. I will come here since the table ends. fa equal 50 divided by square root 2. And if you calculate what is 50 divided by square root 2, oops, I missed it. This is about 35. So the fa and also fb has to be 35 Newton. Why? Because in this case the x components will be the same, and also the y components of the 35 Newton times 2 will be enough to compensate the weight of the body. We can solve another example on the seminar this week. Let's go further. We should be able to divide the force into components like we did here. So from the FA, we need FAX and FAY. We will learn how to calculate motion on a slope. Normally, for example, here's a car, and if the road is icy, means there is no friction. How will this car be accelerated, and by what force? The only force we have is the weight, car mass, times the g, the 10, but it's not the force like the free fall. It's not the force that will accelerate it, only the x or the parallel fraction to the slope. Let's say this is the x-axis, and let's say this is the y-axis. This is the g parallel and this is the g perpendicular. G parallel is g times sinus alpha, since this alpha is also here, and G perpendicular is the cosinus alpha. So based on Newton axioms, the acceleration, in this case only AX, since it won't move along the Y, it remains on the surface of the slope. The AX equal the Fx, the force along X is the G perpendicular parallel divided by mass. So it's G times sinus alpha divided by mass, m times G times sinus alpha divided by mass is G times sinus alpha. So for example, alpha equals 30, the acceleration will be 10 times sinus 30, which is 5. And this is meter per square. This is only with no friction. The only trick, we have to divide always the weight into parallel perpendicular components to count it. Of course, another example, how to play with the force as vectors. If you have two boxes, and if you push it, there will be forces between the boxes, and if they remain together, the full acceleration, remember Newton law said if there is a force acts on the mass, you can calculate like F over m. But in this case, external force acts on the body 1 and not on the body 2. And therefore, we have to divide this problem into two parts. There is an external force on the body 1, and there is a F1 from 2 and F2 from 1. These are force anti-force as magnitude, and their direction is opposite. And what it means, they move together, they have the same acceleration. The only force acts on the body 2 if this F2 or F21, but this is the anti-force of M21, which will decelerate the body 1. So if the x-axis is this one, the acceleration will be F minus F12 divided by M1, and it has to be the same since they move together with F21 divided by M2. Since these F21 is the same, we can say this is a force, let's say it's T over M2. So if we know the masses and the external force, we can calculate the T. We will solve that also on the seminars. So dividing the force into components and also playing with these force anti-forces, with that you can solve some example. A bit more interesting is the friction. You know, you can feel the friction every day. So when you walk, you use the friction between your shoes and the floor to move. This is why it's so hard to walk on ice, because there is only limited friction, so you have to walk very carefully. Technically, we can talk about the friction like forces. At the beginning, when the body, wow, I had to clear the table a bit more carefully, just 1 minute. So we can talk about static and kinetic friction. Static friction, when you try to push a box and it doesn't move. In this case, there is a so-called static friction. And you can imagine the magnitude of the static friction depends on the external force. For example, here we have a box, and describing the friction, the magnitude of friction, we use mu. And we know for static friction, the force is smaller or equal than mu times the perpendicular force. In this case, in most cases, except slopes, this perpendicular force is the weight. So I try to pull it with external force. If my force can be compensated by the static force, it means the box doesn't move. How can that be? That means if I pull with 1 Newton, it has to be 1 Newton. If I pull with 2 Newton, it still doesn't move. It has to be 2 Newton. So the static force, I didn't change anything. I didn't change the mass of the body. I didn't change the mu of the surfaces. So the static force is a force that tries to be equal to the external forces, but it has an upper limit. So let's play with number. Mu equals 0.5 and the mass of the body is 1 kilogram. In this case, this Fs smaller or equal than 0.5 and the G is m times 10, m times G, so it's smaller or equal than 1, 10, 5 Newton. How it works, I go up to 3, 4 and 5 Newton, and at the 5 Newton external forces it still can compensate, but at 6 Newton external forces, since it has to be smaller or equal than 5 Newton, means it's not equal, it can't be 6 Newton since it's an upper limitation. Therefore, the body starts to move. And from here, we can forget the static friction. We have to calculate with the kinetic friction. Kinetic friction is nothing else, just the mu times perpendicular forces. In this case, this is 0.5 times 1 times 10, which is again, of course, 5 Newton. And in this case, the forces of the body will be the external 6 Newton and the 5 Newton backwards from the friction. And if we say this is the x coordinate and this is the positive direction, the Fx, the sum Fx will be 6 Newton minus 5 Newton equal 1 Newton. So if we want to calculate the acceleration, this is 1 Newton divided by 1 kilogram. That will be 1 meter per square. So the static friction can be anything which is the external force with the upper limitation. And if the external force reaches this upper limitation, the body starts to move. And from here, we can calculate only with the kinetic friction, which is a fixed number, so it won't change. And the sum of the forces along the given axis will give you the acceleration. Alright, so this is a summary about frictions. So let's again, normally the mass, the weight starts from the middle, geometrical middle of the body. If I pull something, we start the force at the action point of the body, and the friction always starts from the middle of the surface. Usually we can write P for friction, or if I want to be more precise, I can talk about static or kinetic friction. I think I use all three. So this is how we, so again, from the middle, this is the action point, and this is the middle of the surface. So please do not write the static force here, because it's not a force with the action point on the edge of the body, which is not the connecting surface between the surface. All right, so how can we calculate, for example, this one? I think we will practice it enough on the seminar, but let's start it. So that's another example you will find on the test. I have a body on a slope, alpha, h for the height, mu for the surface, m for the body. I want to solve the equation, so I want to know how this body moves. So at first, there is a weight. We have to calculate the g parallel and the g perpendicular, and right now for the static or kinetic friction. Let's start with the static friction. The static friction looks like smaller equal than mu times perpendicular forces, which is mu times g perpendicular, which is mu times m times g times cosinus alpha. So if I calculate the g parallel and want to check whether it moves, I have to compare the g parallel with the mu times m times g times cosinus alpha. G parallel equals m times g times sinus alpha. So if the static friction is enough to compensate of the g parallel, the box won't move. If the static friction, because of the small mu, can't be large enough and is smaller, it will move. And we always say that this is the x-axis, and moving on the x-axis means sum of x-axis divided by m, and this is g parallel minus the kinetic friction, which is mu times m times g times cosinus alpha divided by m. We will practice on the seminar. So the main thing, we have to be able to divide the vector into components and then understand the nature of the static and kinetic friction, and then we have to do the equations and calculate whether it moves, and if it moves we have to calculate when, for example, will it reach the end of the slope. That will be not that hard, but also not too trivial. I just want to show you that we can play with the forces, with some external forces on the body of the slope. It's a nice example. You can try to solve it, but it's not a must for the first test. So that was the friction. There are other forces in the nature that tries to decelerate the body. So this is, for example, the resistive force. I think I just create the table. So, for example, if you drop, for example, metal ball in the water, in a liquid, so at the very beginning, this resistive force can be expressed by the constant times velocity, and this constant time velocity means the force not only depends on, right now we use only gravitational force, which is a constant, but if the force depends on some kinetical property like V, it means it will be very hard to calculate with, but you can believe me, in this case, if the force, this resistive force, depends on V at a given depth in the water, the force will be close to, will be big enough to compensate the gravitational force, and at the given depth in the water, these two forces will be more or less equal. So you see it's an exponential time, so it's not mathematically equal, but very close to equal. And the velocity of the body won't excess a given, this is terminal speed or settlement velocity and so on. So at a given time, depending on the viscosity of the water and the shape of the ball, at a given time it will stop to accelerate and will move with a constant speed. We used to use it for calculating the viscosity of the fluids by throwing balls. Alright, I haven't checked the Discord. Marvel, any more precise question you want to ask? I can go back and explain. I will continue with the resistive force. So resistive force, technically in the air, it's more complex. So it's not only depend on the velocity, but the square of the velocity. That's pretty hard to calculate. Also the fluid motions. You have to know only two things. There is a so-called laminar flow, when the particles of the fluids move like on the upper plots together. Its velocity depends where this particle of the fluid is in the tube, close to the wall. Since the wall does not move, it has to go from given velocity to the zero, and in the middle, this is the part where the fluid can move the fastest. And this is only true for laminar flow, which is a slowly or not too high velocity flow. At a given velocity, the fluid particles starts to move chaotically, and this is turbulent flow. It's very hard to calculate the turbulent flow, but we live with that. So anytime you fly somewhere, there is laminar plus turbulent flow on the wings of the airplane. So it's a very complex calculation when people try to create a new shape of the wing, which is the better for flying. Alright, so that's all for now. On the practice, we will do example like this, and also example from the first 3 pages. I think that's all for now, and you can ask now. If no question, then you can ask personally in the seminar. So see you on Wednesday and Thursday. Wait another minutes for shy students to ask questions. Alright, so see you in a few days. Bye.